Again, the key idea is going to be the power rule for logarithms, in that if we have the logarithm of a base to a power, we can bring the power down in front times the logarithm of the base. And we're going to use this for every single problem. It's going to be the main theme. Okay, so let's look at a basic problem here. Okay, so here's f of x equals 2x squared, and we want to find its derivative. So this is, again, why I like this preliminary step where we look at the function. Now, when looking at this function rule, we notice in particular that the power depends on the variable x. And so none of the basic differentiation rules apply. So we're going to need to modify this function slightly so we can use the basic rules. Again, we don't need to reinvent the wheel. We just need one preliminary step and everything will work in a standard way. So again, I noticed the base is in e. If the base is e, I could just use the standard rules. The derivative of e to the x is e to the x, and use the chain rule with that. But if the base is not e, then we need to use the logarithmic differentiation technique. So how does that work? Well, here, this is our preliminary step, and this is what we need to do. So here's our function rule. So this is in the form of a base to a power, where the base is 2 and the power is x squared. So what I want to do is I want to apply the logarithm of both sides. Apply the logarithm of both sides. Now the power rule for logarithms looks like this. Now again, in our problem, we had a base of 2 and we have the power is x squared. So we just plug in. 2 to the x squared is going to be x squared times log of 2. And that's how we derive this step. And this is where we're going to do the differentiation on. So we're not going to differentiate, apply the differentiation rule directly to the function. We're going to apply it to the log of the function. And that's the only difference. It's going to be exactly the same, standard. And this technique works for every single log differentiation problem. Again, usually what people have you do is just memorize every possible formula. But this one technique works for every single problem. And don't be excited about something like log 2. Log 2 is just a number. It's approximately 2/3. It's just a number. It doesn't log 2 so what? It's about 2/3. So this is our preliminary step, right? This is instead of doing the algebra, instead of writing square roots as a power 1/2, and instead of the simplifying. This is what we do for our base step here. So instead of working with the function directly, we're going to work with the logarithm of the function. That's it. That's the only difference. So we're going to take the derivative of the logarithm of the function. And again, we replace it with its definition, log 2 times x squared. And you can see this is just going to be a constant times x squared. So we can use the standard differentiation rules, right? Take out the constant. The power rule is going to be derivative of x squared is 2x. So there's nothing wrong on this side at all. And you'll notice the left-hand side, this is just, again, what's the only possible rule that we can apply here? The only possible rule that can apply to the left-hand side is the chain rule. So this is really just implicit differentiation. And you'll see the number of possibilities that come up here are really fairly limited. You do a couple of the homework problems, work out the problems here, you'll see it's almost always going to be, it doesn't have to be, but most of the time it's going to be derivative of log fx. So this is going to be pretty standard. So if we're going to use the chain rule for this, we need functions, our functions f and g. Since I have a function in here, I'm going to call them capital F and capital G. That's the easiest way to get around the notation. So I'm going to take capital F, the outside function, to be log of y. And I'm going to take the inside function, okay, I'm calling it big G. Maybe I should have called it G here, but f of x. And you can check that, in fact, that gives us the correct expression, or my correct choices of f and g. So once again, if I'm going to use the chain rule, I'm going to take the derivative of these functions. So the derivative of the logarithm is going to be 1 over y. The derivative of capital G is going to be, again, I could have just called f g maybe, but that's fine. The derivative gx is just going to be f of x, fx I mean. And I'm just going to plug it in directly into the chain rule. So here's my table of data. and I'm just simply going to plug it in. Gx is fx, g of x is f of x, f of y, fy is 1 over y, so I just fill it all in. And it's going to come out here. In fact, this is going to come up in most of the problems, and you can just remember that the derivative of this is 1 over f of x times fx x of x. It's going to come up so often, you'll just pick it up by doing the problems. So if we go back to our original problem again, you might work this out on the right side of the page, but after a few problems, you'll see this is always, it doesn't have to always come up, but it comes up a lot. This is 1 over fxx. Now notice what we want is fx, not 1 over fx, f of x, right? So what I want to do is I want to just solve for this. I'm going to multiply both sides by f of x, right? So again, I'm just cleaning the page here. I just want this. So we're going to multiply both sides of this equation by f of x. And so now what I'll do is, and again, it always works like this. It's always going to work like this. I'm just going to substitute the actual rule in for this, right? This is the definition of f of x. And so you can see what and so this is what you have. And you should always look. You can always look to see your form. Your form is always going to look like the derivative is going to have your base function in here, and then it's going to be like something like a fudge factor out in front. So the derivative is going to be the base one and a fudge factor. And that's it. They're all going to have the same format. Now here's another problem, and we can see again, the base in this case is x. That really doesn't matter. But the power here depends on the variable, right? So we're going to have the same technique here. Okay, so why don't you guys give the video a pause, follow the exact same steps in the previous example, and you should be able to go through it. They'll all have the same general features. So good luck on that. Pause and give it a try, and then we'll start up again. Okay, let me come back. What we have is I'm just, again, doing my preliminaries here. We noticed that the power depends on the variable, and of course the base is not e. So once we see the power depends on the variable, the base is not e, we can see we want to put it in this form and use logarithmic differentiation. It's just a template. All the problems will do exactly the same. For us, the base is going to be x, and the power is going to be x as well. That's fine. It's fine. So now the idea is to take the logarithm of both sides, right? Take the logarithm of fx and substitute in. Notice this is the power rule for logarithms here. Our base is x, our power is x, just substitute in, and we get the following. So log x to the x power is going to be x times log x. And this we can deal with. Well, this we can deal with the basic rules. So instead of dealing with f of x equals x to the power x, what we're going to do is we're going to deal with this expression in its place. We're going to deal with the logarithm of the function. And that's what we're going to do. Again, it will always work in the same format, and you'll always be able to use the basic differentiation rules. So I'm just simply going to take take the derivative, of both sides, just as we did in implicit differentiation. And you can see on the right side, again, you can try that. You can try this. So why don't you pause the video if you haven't gone through here, and work the right side out, and come back. Okay, so if you look on the right side, the only possible rule you can use here is the product rule, right? It's the product rule. So you don't really have any choice in the matter. So just using the product rule, we develop the right side into this expression. And again, log x, this is standard. Derivative of this, we have a formula for. X to the first power, we have a formula for. So the derivative of log x is 1 over x. Again, this is fine. We're only talking about positive values of x. This was stated in the problem description. The derivative of x is x to the first power is 1. And so the right-hand side is all worked out. And as we said before, the derivative of log fx, this came up in the last problem, and it's going to come up in a lot of problems. It's possible to rig problems so it doesn't happen, but really that's going to be the exception, not the rule. You'll do enough of these where you can just remember this formula. So the left-hand side we take care of like this. And we can simplify now. We need to solve again for just fx. So what I'm going to do is we'll multiply both sides by f of x as we usually do. All right, and then we substitute in the rule that we're given here. Right. So this is again going to be the standard form for these problems. And once again, you're going to see that it's going to be the original function. So the derivative is going to be the original function and some sort of a fudge factor, right? One would be unity is the base, and this is going to be the fudge factor. And they all have this flavor to them. This problem's, again, we can handle this. It looks a little odd at first. Again, I'll give you a moment. Pause the video, try it, see how you can do. Again, if you have problems, that's fine. Learn by your mistakes, but give it a shot. Okay, let's look at the basics again. I always like this preliminary step, and this is exactly one of the reasons why this is useful. I'm telling you the domain here, so you don't even have to worry about that. Notice that when you write sine x of x, what you're really saying is the power is x, right? So it's sine of x, all that raised to the power x. So again, we see that the variable, the power depends on the variable, and the base here is not a. So we know we have to use the logarithmic differentiation technique. That's fine. Now, if you didn't know that, pause and try it again. Otherwise, let's go. You know it has to fit in this form. It has to fit this template, m to the power p. So I'm going to take the base to be sine x, right, sine of x, and the power is going to be x. At this point, everything just falls into line. We'll take now the logarithm of both sides, right? Take the logarithm of both sides, and we're going to use the power rule for logarithms. We're just going to apply it directly. The base is sine, the power is x, and so the x comes down in front, and we have this form. And so instead of working with our original function f of x, we're going to work with logarithm of f of x, and that's what we're going to use. So again, this is just done in your preliminary step. So instead of working directly with f of x, we're going to work with the logarithm of f of x. And it should proceed exactly as before. So again, you could pause and give it a try. So what we have is I'm going to take the derivative. Again, this is just implicit differentiation. On the left, you can see that I'm going to use the product rule first. Right? I'm going to use the product rule first. The derivative of x is 1, so that's easy to deal with. There's nothing to do with the log sine x term. This is going to be an issue, and we'll worry about that later. And this side is going to be, again, fairly standard. So the derivative of x is 1, right? And this is the term now I'm going to worry about. So again, I don't want to do it here. Let's just fold the paper in half, do it on the right side of the paper, and deal with it. You can look at this and you can see there's no rule that applies directly to this. It's not log of x. The only rule, none of the basic rules apply directly to this. The only rule that can possibly apply to this is going to be the chain rule. So okay, just on the other right side of the paper, we're just going to look at this separately as a chain rule problem. And here it is. Let my function h be the logarithm of sine of x, and we want its derivative. Again, you can pause and try it yourself. We're going to have f of y being the outside function is going to be log of y. G of x is going to be the inside function, the x part of the function, sine of x. And again, this is more typical of what you might just simply write down. You don't have to write a book. If I have f of y is log y, then its derivative is 1 over y. If I have g of x equals sine y, gx, its derivative, is going to be cosine of x. And then plugging everything into the chain rule, we get, again, it doesn't matter if you call it cotangent, cosine over sine, a cotangent of x, whatever, that's fine. So again, you don't need, the chain rule doesn't have to be written out. These lines don't have to be 20-minute problems. You should be comfortable with doing something like this. But once I obtained this derivative using the chain rule, I'll just come back to my original problem and plug that directly in. And again, it's fighting smarter, not harder. No single step should be all that complicated. Now we'll look at the left side, and again, this has come up a lot. Already it's come up in the two previous problems, and it's fairly standard. So the derivative of log f of x is 1 over f of x times fx. And this is just, again, the chain rule. It's implicit differentiation, and I did it in the first example. It comes up quite frequently. Again, we need the derivative, right? I'm looking for fx. So I'm just going to multiply both sides by f of x to clear this out. So this is where we left off. I had to clean up the slides, right? The dot, dot, dot. This is where we left off. I'll multiply both sides by f of x, right, to clear that. And again, we have a fudge factor here. We're just going to obtain this from our original problem, from the original description of the problem, and plug that in. And again, everything always has this same basic form. The derivative will be the original function times some sort of a fudge factor in front here. Okay, now here's a more general problem. Again, jump in, follow the rules. Don't go getting crazy here. Just jump in, follow the rules, and see where it takes you. Again, if you have trouble, that's fine. That's why we're going to work those out. So take your time and give it a shot. Okay, let me come back. Here's our rule. There's nothing I can do to simplify this immediately. You see, there's various things in here. I tell you the domain, so we don't have to worry about that. I'm just going to apply the differentiation, again, just as we always do. If I want the derivative, it's derivative of the function. I'm just going to substitute the rule in of the function. Notice I'm not going to jump in and take logarithmic differentiation first. It doesn't seem that it's a base. There's nothing that's a base to a power overall. I'm just going to plug this in, and then I'll look at it. They're pluses, pluses, pluses. It's just going to be the use of the sum rule over and over. So I'm dividing and conquering. Instead of looking at one giant problem, I'll look at it 4 basic problems. And you can look at this and you can see what's happening. Pi squared, remember pi is about 3. This is just a constant that's about 9. The derivative of a constant is 0. This term here, derivative of x squared, that's going to be 2x. So the first term and the third term are really just standard derivatives. There's no big problem going here. Don't turn the problems immediately into a disaster area. Just take it as it comes. Now, 2 to the x, you can see the base is not a. The power depends on the variable. So we're going to need logarithmic differentiation to take care of this term. And the last term the same. So we'll cross that one bridge when we get there. Okay? So we'll just break them all down. I have 4 separate problems. The derivative of the constant, again, this problem, 2 to the x, x squared, and x to the 1 over x. It's just 4 different problems. Instead of 1, we have 4 different problems. That's fine. The derivative of a constant is 0. Again, don't make a mountain out of this. The derivative of x squared is 2x. So far, so good. And we'll concentrate on this as a separate problem. We'll just fold the paper in half. No sense panic about it. Let's look at it specially. So in this case, what do I have? I have the function is 2 to the x. I want its derivative. So we'll just follow the exact same process that we've done. In fact, I think we did this problem already, but it's good practice. You can try, pause the video, give it a shot. 2 to the power x, right? We're going to take log. We identify the base as 2. The power is x. I apply logarithms to both sides and the logarithmic power rule. So instead of dealing with this function directly, f of x equals 2 to the x, I'm going to deal with the logarithm of f of x, which we can see is just going to be a constant times x. Right? So I'll take the derivative of both sides. This is exactly what we did with implicit differentiation. Take out the constant log 2. Derivative of x is 1. And on the left side, we have the derivative of log fx, which again I did in the very first example, but it's always 1 over f of x, fx of x. I want to solve this for fx, so I multiply both sides by f of x, and I'll substitute in the definition of f of x is what we're given. So again, what we see is we have a fudge factor times the original function. And now we'll just simply take this from the right side of the page and plug it back into where we left off. Again, it's just divide and conquer. Work smarter, not harder. Now we'll focus on, let's see, I'm just rewriting it all over here again to clean it up. We'll focus on this term. So why don't you take a minute, pause the video, and try this. Again, it should be exactly the same steps, and then they'll come back. Okay, here we go. Once more, we identify the function. This is its own separate problem. No need to do it all in one step. And again, I notice that the power depends on the variable. So it has the form MP, right? Base power. The base is x. That's fine. That really doesn't matter. The key feature here is the power depends on x. Okay, it's 1 over x, but it's all the same. Using the power rule for logarithms, I bring the power down in front. And so this is the expression we're going to work on. And again, I like writing it as, instead of taking it as 1 over x, again, write it as x to the minus 1 power, right? I mean, this is back to basic differentiation techniques. X to the minus 1 is, I think better than writing it as 1 over x. So we're going to do differentiation on this. So we take the derivative of both sides just as we would with any implicit differentiation problem. Now we're going to use the power rule here. Of course, you could have just kept it as 1 over x log x and use the quotient rule. That's fine as well. It's much more probably of the style idea. But I prefer the power rule. So just applying the power rule, we obtain this expression. The derivative of x to the minus 1, the derivative of log x is 1 over x. The derivative of x to the minus 1 is minus 1 over x2 squared, but based on the power rule. I can clean this up with algebra and so forth and so on, but it's not a big deal right now. And once more, the derivative of log f of x has come up in every problem we've done so far. So I'm not going to rederive it. It's just 1 over f of x times fx of x. Again, in the same way it's always come up. So just cleaning it up, I want to shorten it, just focus on where we are. I want to solve for fx, so I'm going to multiply both sides of this expression by f of x. Right? And you want to make sure you multiply everything on the right by this. That's why I have the extra brackets. And then we'll simply substitute in our rule. And that's it. I mean, again, you can clean this up if you like. You can clean up the inside. That's fine. But essentially what we have is a fudge factor times the original function. I just played around with the algebra here, guys, because it's not bad for you to get comfortable with it. I gave you the cheat sheet, the first page of which has these algebra expressions. So I'm just bringing this over here, and then I'm just going to have x to the power over x to a different power. I'm just using the various algebra expressions. I'm getting a common denominator, and I'm just going to clean all this up. You don't have to do this. Certainly, I wouldn't do it for a test. But answers in the back of the book are often like this. And again, you're not going to get stronger with algebra if you don't do it or if you just avoid it. So I just put it in there as just a means of having you practice with the algebra. That's all. It's not a big deal, but you're not going to get stronger if you don't practice the algebra. So I have this expression now, and I'll take it back and I'll plug it into my original problem, right? This is the problem we're working on. Again, I just suggest you fold the page in half and put all that work right on the side. And then we'll just plug that in right here. And that's it. We just have to clean everything up. I don't know how much you can really clean up here, but you just clean everything up and you're done. So again, is it a tough problem? Really, it's 4 problems, right? 2 of which are pretty easy, 2 of which involve implicit differentiation. So it's not the world's easiest problem, but it does follow a standard template. Okay, the next problem is getting a little more challenging. Again, I'll give you a chance to try it. Take a moment, follow the steps, and you'll be fine. Just practice. If you make mistakes, that's fine. Okay, let me jump in. Again, I'm looking at the function and I notice that in fact the power does depend on the variable, right? The base is not e. So I want to take a preliminary step of taking the logarithms, right? My base in this case is the 3x squared plus 5, and my power is 1 over x. So I have the form of a base times a power. I'll take the logarithms of both sides, right? And I'm going to use the power rule of logarithms, which is written here. So I have my base identified, I have my power, and I'll just plug into the formula, and I see that log f of x now equals 1 over x times the log of the 3x squared plus 5. And I'll do my differentiation on this. Again, I prefer to write 1 over x is x to the minus 1. That's my style. I prefer to use the product rule as opposed to the chain, as opposed to the quotient rule. I mean, I almost never use the quotient rule myself. So again, that's more a matter of style. But instead of dealing with the function f of x directly, we're going to deal with log of f of x, right? That's the key. And this is just an implicit differentiation problem. So again, if you haven't done it, pause and jump in and try it and restart the video. Okay, so I'm just going to take the derivative operator of both sides, and I'm going to have a log of f of x here and the right side. Looking at the right side, I can see that what I have is the product rule. Again, if you wrote it as 1 over x, you'd have the quotient rule, but I'm going to use the product rule on the right, and I have this. And again, looking at these terms, do the easy things first. The derivative of x to the minus 1 is pretty straightforward. Then I'll come back. Just using the power rule, I take this one out. And now let's focus our attention on the next term. Now, again, if you look at it, the only possibility here is the chain rule. It's the only the only rule that we can apply. So let's break this off on the right and just look at it as a chain rule problem. If you haven't done so, try it. It shouldn't take an hour. It should be literally a couple minutes, and that's all this takes. So give it a shot and then restart the video. Again, this is really all I need for the chain rule. Maybe it's more than you even need. But anyhow, my function is going to be log of 3x squared plus 5. I have to identify a function f and a function g such that h equals f of g. G is going to be the g of x. So I'm going to take the x material, 3x squared plus 5. That equals y. So f of y is log y. Once I have the function f and g figured out, I take their derivative. So f is a function of y. F of y is 1 over y. G is a function of x, so gx of x is just going to be 6x. Again, I don't need to make a meal out of this. If it's not that complicated, by all means, you don't need to put in every step. I'm going to apply the chain rule over here. Just plug in my terms, my gx, my g of x. And I come down to this. And again, I think this is more than adequate for what, for example, for a test or something. You don't have to write it all out. And this problem really, realistically, should not take more than a few minutes for you, okay? So if you're really struggling on this, maybe go back and practice some more chain rule problems. But we're going to take this now and go back to the original problem, right? Here's where we left off. And I'm just going to plug that in here, right? This is what we did on the right side of the page. I'm just going to plug it directly in here. And so the calculus is done on the right-hand side. Again, we could clean up the algebra, that's fine. But the calculus is finished on the right side. On the left side, again, if I'm going to do this, I'm going to use the chain rule. But once more, you notice it's the standard form, the derivative of the log of f of x. This has been in every problem we've done, and we did this calculation in the very first one. So the derivative of log f of x is 1 over f of x times fx. I'm just going to plug that in there. So let me just clean all this up again so the slides are getting a little busy. What I want to do is find fx. So I'm going to multiply both sides by f of x in the usual way, right, to clean it all up. And then I'll substitute in the rule for f of x. Right, so again, you're going to have the original function times a fudge factor. And once more, you can clean this up. I don't know. I don't really see anything more here, but it's just algebra. It's good to practice the algebra, but you don't have to make a big deal about it. And so that's what we have for our answer. Now here's another problem, and again, this is getting a little more difficult. I mean, again, the technique itself isn't changing, but to be fair, the problems I'm giving you are getting a little more difficult, and that's the problem. That's the issue here. So just follow the standard form, and I think you'll be fine. So again, give this problem a try. Don't go crazy, just the basics, the basics, the basics, and don't hesitate to make a mistake. That's fine, that's how you learn. Okay, so hopefully you've tried it, but let me jump in. I'm going to look at this. Now, this isn't, clearly something's happening. The powers depend on the variables, but this isn't of the form of base times a power. So let's just go with it. We don't have any log differentiation to begin with. I'm writing this as f of, standard. The derivative comes out when the derivative of the function is the fx. I'm just substituting the rule in here. Now, again, I probably should have done this in the preliminary step, but you could use the quotient rule, right? You could use the quotient rule. I just prefer the power rule, so I took the whole power up. I mean, it's just my preference, just my preference. And so what I'm going to do is I'm going to use the the product rule. I'm going to use the product rule at this stage and just write it out like this. And you can see I broke the original problem into two problems now. I have to concentrate on this piece, and I have to concentrate on this piece. And again, they look intimidating, and maybe, but we'll just deal with it one at a time in a standard fashion. There's no reason to get excited about it. So again, why don't you guys jump into this? We notice that we have a power that depends on the variable, right? And the base here is not e, so this is going to be a log differentiation. So just break this off and do this separately, and I'll pause the tape and come back, and I'll do it again in a moment. Okay, this is what we have. I guess I should have called this h. It's a typo, right? If I'm looking at derivative h, I should have called this h. That's fine. Or I guess I'm calling it f anyway. We know the base, the power depends on the variable x. The base is not e. So if I come over here, I can see the base is log x, right? The base is log x, the power is x. Taking logarithms of both sides. Now, don't be intimidated. What does it mean to be log of log? I don't know. I don't really care. It's not that big a deal. Just apply the rules correctly. I identified the base as log x. The power is x. So I'm just going to plug this in directly as I have it. And you're going to have x times log x. Again, what does this mean? It's purely artificial. I don't know what it means. It doesn't really matter. We're not in a philosophy class. We're not debating what this means. It doesn't make any difference. So instead of dealing with this expression, taking the derivative of the function, we're going to take the derivative of the logarithm of the function. And we'll just write it and see where it goes. Again, I'm not saying this is easy. This is on a more challenging side. But just have faith and follow. So if I look at this, I can see that I'm going to use the product rule. So again, without making a big deal about this, I'm going to use the product rule. Again, I don't want to stress about it. Derivative of x is 1, right? Now I'll work on this piece. And you can see that's not trivial. But again, it has to be one of the differentiation rules from the crib sheet. The only one that's going to apply is the chain rule. So take a moment, this is nothing more than a chain rule, and apply the chain rule to this piece, and then come back and plug it in here. So pause the video and then try it. Okay, let me do it. I'm going to have log of log x. So if I'm going to use a chain rule, I need functions f and g such that h equals f of g. I'm going to take g of x to be log x. I'm going to take f of y as log y. I take their respective derivatives. The derivative of log x is 1 over x. The derivative of log y is 1 over y. So this is my data. I'm going to plug it directly into the chain rule formula to get this expression here. Again, if you hadn't done it, give it a try. Make sure you're comfortable with that. Each step, again, the problem overall is very intimidating. But we fight smarter, not harder. Each derivative is very basic, and all we're doing is the chain rule or taking the logarithm and doing derivatives. Now I'll take this expression and plug it back into, well, where we left off, right? So you would have done this maybe on the right side of the page. Just directly come over here and plug it in, right? You just directly plug it in. So the right-hand side is completed, right? I mean, yes, we can clean up some of the algebra, so forth and so on. The left-hand side, again, this is popped up in every single problem we've had. So the derivative of log of f of x is 1 over f of x times fx of x. And again, let me just clean up my slides. We want to solve for fx. Right? I should have fx here. So I'll multiply both sides by f of x. Right? And I'll substitute in from the definition up here. Right? So again, you're going to have the original function plus a fudge factor. And again, what does all this mean? I don't know. It's just a made-up problem. It's just a mess. It's a made-up problem. I mean, who cares? Okay, so let's take this then and go back to the original problem. So in our original problem, we had this, right? And so just substituting in what we found over here. Actually, I think my domain, this x should be greater than 1, so I guess that's another typo, right, for this. But at any rate, this is what we have, and it's a gigantic mess. It's a gigantic mess. But again, all the calculus is completed on the right-hand side. Now we have to worry about this term, right? So we'll look at this term now. And again, this is going to be a problem. So let's look at this separately. We can see that this is a base to a power, so this is going to also be logarithmic differentiation. So why don't you guys pause the tape and give this a try, and I'll come back and do it. Okay, again, I have a base to a power. Again, this is a typo, this should be f, but I have a base to a power, so that tells me the base is not e. So this tells me that I'm going to use logarithmic differentiation. I identify the base is 2, and the power is minus 3x plus 1, right? Minus bracket 3x plus 1 on bracket. Take logarithms of both sides, right? I'm going to bring the power down in front. So log 2 again is going to be a constant. And we're going to work with the log of the function instead of the function itself, right? So instead of working with the function, we're going to work with the logarithm of the function. Now we'll take the derivative of both sides, right? Log 2 is a constant. Just bring it out in front. This expression is just a polynomial, very easy to take the derivative of. Again, we don't need to make a project out of it. 3x plus 1, the derivative is 3. The left-hand side is, again, it's popped up in every problem we've done, 1 over f of x times f of x. And again, there's a way of doing it. We did it in the first example, but again, it comes up all the time. You know, you pick it up by osmosis. Solve now, right? Oh, you can clean this up again. I mean, I'm not a big fan of this, but sometimes people are, right? I mean, you can go backwards with this. The base is 2, right? The power, right? You're going from this side of the expression to the left side. So you can write this as log 2 cubed, right? Which is 8. Again, I don't know. It's cubed, I don't know. Now we'll multiply f of x over here and then substitute in the rule. So this is where we left off. I'll substitute in the rule for f of x, and there you have it. Again, for the test, I mean, we're not going to take all points for something like that. But again, some people like that. That's a big thing. So again, it's not bad to be aware of that. So once this is done, I'm going to take this and put it back into the original problem. So this is where we left off, and I'm going to just substitute that back into the original problem, and that's it. I think all the derivatives are done at this point. That's a tough problem. But what I want you to understand is if you just break it down piece by piece, it's doable. I'm not saying it's not difficult. I am saying it is doable. Okay, so you just have to be careful. You just have to be organized and neat, and you can get it. But yes, that is a very difficult problem. Here's an implicit differentiation version of this. So again, this is an algebraic equation that defines a function g of x implicitly in a neighborhood of the point e0. Again, e is about 3. And I want the slope of the tangent line because I want a linear approximation for this function. So we'll proceed with this exactly how we did. Give it a shot. It's going to be handled exactly like we did implicit differentiation. And one step at a time. So give it a shot. If you get stuck, come back and check with me. Okay, here's the picture. So again, I did the green line, or the red line, I guess, is G, by the fundamental theorem of calculus idea. And the green one here is going to be, I guess, the tangent line, the linear approximation. And again, you don't have this explicitly, but you can see it's a pretty good approximation in the neighborhood of this point. And whereas you don't, this is complicated. Okay, so let's go in. Again, I have a function g somehow specified in a neighborhood here. I guess I should have, this should be a neighborhood, this should be the domain across the range, but in a neighborhood of this point, the neighborhood here specifies a function. So again, what am I going to do? When we do implicit differentiation, I don't want x's and y's. You have to have a single variable. I'm going to replace y with g of x just as we always do with implicit differentiation. Again, I don't need to think about it. It's what you do always with implicit differentiation. And then with implicit differentiation, what am I going to see? I see now that the power right here depends on the variable x. So what I'll do is I'll use the log power rule. So I'm going to bring this down, right? The base is x, the power now is g of x. Again, I don't know what g of x is, but it is a function of x. So I'm going to instead use the logarithmic expression here. So instead of using the log x, I'm going to do the logarithm of both sides. And now I'm going to do implicit differentiation on this side. Okay, so let's just jump in and see how we do with this. All right, take the logarithm on both sides. On the right side, you can see I'm just going to use the power rule, right? The power rule. Now, just as we did with implicit, I'm not going to worry about what gx is. I don't know. The derivative of gx then is going to be gx. The derivative of logarithm, of course, 1 over x. The derivative, I guess, here is gx. So the right side is done. Again, I don't know what g of x is or gx of x, but it'll work itself out when we plug in the data. Now we have to look at the left side. And this is nothing but, this is going to be a chain rule problem. I think it came up previously, that's why I have it, or else you can take a time and work it out and see if you get this. So this is it. All the derivatives are taken out, all the calculus, is done at this point. So with implicit differentiation, what are we going to do? We're going to plug in the data, right? We're just going to simply plug in the data. So I'll plug in, here's the expression where we left off. I'll plug in the data x equals e. Everywhere there's an x, I'm going to substitute an e, right? G of e we have is 0. So wherever I have g of e, I'm going to make it 0. And I noticed that the log of e, the natural log of e, is 1. So things are cleaning up. And so you can just solve it. This is 0. 1 times gx is e is 1. So this is 1 over e. That's about a third. So the derivative at e is 1 over e. So we do have our slope, right? Change in y, change in x, the slope of the tangent line when x equals e, and that the point e0 is going to be 1 over e. And then the next problem, of course, will be find the tangent line and the linear approximation. And I didn't do that, but you can do it. And if you go back to the original and plot it out, which I did, you can see it's pretty good. I mean, you don't know what this function looks like, but you have the linear approximation, which is a very good guess on this neighborhood. And that's why. And again, if you wanted a better approximation, you could take the second derivative and so forth and so on. So again, this pretty much encompasses all the problems with logarithmic differentiation. Don't be intimidated. Try some of the problems. Just try to follow the template, right? Break things down. And some of the problems in this section, admittedly, were a little hard, right? They're on the challenging side. But don't be intimidated. Just try some of the problems. If you're having trouble, then get a hold of us. But you should be all right. Okay, good luck with that.